show. I want to show some slides here. I worked on this example about 10 years ago, but I just want to explain what it does or how it works. It's just so you have a basic understanding of it. Oh, with envelope. Well, first of all, who's doing envelope tracking today, or who's working on that? Just a few of you. Okay, so for those of you who don't know envelope tracking, the idea behind it is that it's a method of improving efficiency. And you have a modulated input signal which may have a high peak to average power ratio. When the amplitude is low, we can set the drain bias of the PA down, and the power consumption is lower. So, but when it's high, we can have the drain bias at a higher level. So we can just have the drain bias of the amplifier track the amplitude of the input signal and just keep it operating more efficiently. Though I've been able to simulate this sort of thing in ADS, but it's still somewhat ideal. The way this works is there's a block that uses equation-based models to detect the power, and then based on the power, well, okay, so what you have to do is you have to simulate the PA, say, gain versus bias voltage, and then you generate a shaping table from that so that you can keep the amplifier either operating at high efficiency or at constant gain as you change the input power level. You can adjust the bias so that the gain remains constant, so you minimize distortion. So you can get the shaping table from harmonic balance simulations, and I'll show how to do that. Once you have the shaping table, you can apply a modulated signal, detect the signal power, apply that power to the shaping table, get a drain bias voltage, and apply the drain bias to the amplifier. Then, if you want to, you can run simulations under ideal conditions where, basically, this is a bias modulator, and you can have this be completely ideal and see what the results are, or you can introduce a time delay between the input signal and the application of the bias, or you can introduce a slew rate limit to the signal, the bias voltage that you're applying, or you can introduce a band limit to the signal. And I think you can introduce other distortions to the bias signal as well. But I don't have an example of, my understanding of envelope tracking is that a big part of the design task is getting the bias modulator to work correctly. And I have never created an example of a complex bias modulator. So I don't, probably some customers have, I don't know. I assume it's proprietary, certainly what customers have done. And I think there are limitations as to how well you could simulate that with ADS, but it is also possible to take a modulated input signal, and you have, say, power versus time. this has an envelope, so you have power versus time, and the bias modulator needs to output a bias voltage versus time that tracks this signal. So I can imagine simulating the bias modulator separately, with an envelope input and generating a bias voltage versus time. So you can have a separate simulation where I have a modulated signal and then I have a corresponding time domain signal that I'm applying to the bias, and you can the bias time domain signal could have distortion added to it. So that's possible to do, and I have an example of that. But it's like two separate problems. You have some time record of a modulated signal. Maybe your bias modulator is a different simulation, so you're applying the envelope of the input signal to the bias modulator. You get a time domain waveform. It has some distortion because the bias modulator isn't ideal, and so you can read in the distorted time domain signal and apply it in a separate simulation along with the modulated signal and see what the results are. So that's possible to do. And this is this just gives you an idea of what it looks like to generate a shaping table. I'm sweeping the bias of the amplifier from one. This is a fairly small signal amplifier. It's not a real high power amplifier, but from 1.5 up to 6 volts. And this is the power delivered. So this value and the gain is constant in this case at 11 dB. So you can subtract the gain from the output power and get the corresponding input power. So you have these bias voltages and input power. So for a particular input power, you need to set the, okay, so let's just say this value minus 11, so when the input power is say about -1 dBm, we need to set the drain bias to about 1.5 volts to get 11 dB of gain. Then when the input power is 15 minus 11, or about 4 dBm, we need to set it to 2. So this gives you an idea of how you need to adjust the drain bias as a function of the input power. And that's just what this is showing here. Okay, and you can have different, like in this case, the drain bias or the constant gain is reduced to 10 dB. So you get this shaping table, and you could have a shaping table to try to maintain constant compression instead. So in this case, the gain compression curves are plotted. And in this case, it's set to 1.5 dB gain compression. And now the gain is a little bit different. It's not constant anymore, so there's a little bit of variation. But certainly, ADS could be used to generate shaping tables. Okay. But I have simulations of, like, for comparison, I think you need to simulate the PA under constant drain bias. So here this is a fixed drain bias, so I think it's useful to compare the results against this condition, the simple condition. The envelope tracking should improve performance. then this is the tracking model. This is an ideal model. And we detect the signal here, and then these equations just detect the power and feed the power into the input power, the envelope of the input power, and get out the bias voltage that corresponds to that input power, and apply that to the drain of the PA. It just uses the data access component to do that, to read out the shaping table data. And then you can introduce non-idealities. You can introduce a finite slew rate in the bias modulator. And then that will distort the signal. So you might get a result like that. You get this certainly just distorted AM to AM curve. You can have a time delay difference between the RF and the bias modulation, and that will introduce significant distortion. So it's, well, let me just pull up an example here. So there are several examples on our Knowledge Center that you can download. This is a comparison between so this is an LTE signal with a fixed bias in red, and the blue is an LTE signal with an 11 dB gain envelope tracking shaping table, and there's a noticeable improvement in the power added efficiency. And this is the EVM versus time plot. So yeah, I think these are useful, but they're certainly not a complete solution for envelope tracking. But I think they're still somewhat useful. So hopefully, if you need to do envelope tracking simulations, hopefully this is a suitable way to do it for you.
네, 그 입천시 높이 규합 그 이벨롭 트래킹 시뮬레이션에 대한 간략한 개요 컨셉과 개요를 담은 예제를 소개를 해드렸고요. 저희가 이제 그 인풋 쪽에 모듈레이티드 시그널을 넣는 경우에 이제 그거에 이벨롭을 어떻게 디텍팅을 해서 바이오스 회로에 적용을 해서 그 효율을 높이는 그 하는 부분에 대해서 잠시 설명을 드렸습니다.